Jnanam paramam dheyam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. We have been discussing transition metal cyclopentadienyl hydride complexes in the last lecture as a part of our overall treatment of this topic on half sandwich complexes. In that respect, we had talked about transition metal cyclopentadienyl carbonyl complexes, followed by transition metal cyclopentadienyl nitrosyl complexes, followed by transition metal cyclopentadienyl hydride complexes, which we would be continuing discussing upon, and then we will take up another in this series of half sandwich complexes, which is transition metal cyclopentadienyl halide complexes. Now, these are half sandwich complexes, they are heterolytic complexes, and they offer a large reactivity pattern which are kind of unique to them. Now, in our continuing with our discussion with transition metal hydride complexes, we have in the last class we have looked into their synthesis as well as their reactivity pattern, and then we have also looked into the characterization of this metal hydride moiety by using NMR as well as IR spectroscopy. Now, what we had seen is that these metal hydride complexes are primarily observed for 4D and 5D transition metals which are electron rich, whereas for 3D transition metals which are electron deficient, usually observation of these metal hydride complexes are rare, as they are unstable, and they may, even if they are formed in situ, they eliminate hydrogen to give the dimerized product containing 2 metal center, but the hydride moiety eliminates as hydrogen. Now, from that perspective, the metal hydrides are usually stabilized for more electron rich 4D and 5D metals, where they could be isolated in the monomeric form. Now, as a result of this metal hydride moiety being attached to electron rich metals like 4D and 5D, the metal hydride moiety is very basic and hydridic in nature, and that can be experimentally verified by treatment with acid, where these hydridic moieties can easily be protonated. And we had seen reactions to that effect for molybdenum, tungsten and rhenium. Now, one of the classical metal hydride moiety which have been extensively studied is BCP rhenium hydride, and we had discussed about the hydridic nature of this proton. Now, this molecule can be easily protonated. Its basic strength is comparable, it is highly basic in that, say, highly hydridic in nature, and the basic strength is comparable even to a strong base like ammonia. Another interesting thing is the reactivity of this metal hydride, and because of the reactivity one can see isolation of very unstable compounds, and such an example is for happens is for this 3D metal hydride which of titanium. So, for example, Cp2 titanium hydride is unstable and primarily because it is of 3D metal, and similarly BH3 molecule also is unstable. However, these two molecules combine to make an adduct and they are stable in an adduct form. I am going to illustrate this through the example given over here. So, Cp2 titanium dichloride in presence of NaBH4 eliminates half hydrogen, half B2H6 and 2 NaCl to give this titanium PCP hydrogen, boron, hydrogen, hydrogen, boron, hydrogen, which is the titanium boronate. So, what is remarkable of this reaction is that two entities, which is BCP titanium hydride, which is the one over here, and the BH3 molecules, which also is unstable, two unstable entities get stabilized by this adduct form, and this happens as a result of 3-centered 2 electron non-classical bonds, electron 3-centered bridging hydride. So, this is an important aspect of transition metal hydride chemistry, and what we saw in this nice example that unstable cyclopentadienyl titanium hydride, which is a hydride of a 3D metal, can even be stabilized in presence of boranes BH3, which in its monomeric form is also unstable, by formation of an adduct of BCP titanium hydride and BH3 through this non-classical 3-centered 2 electron bridging hydride bond. This reflects on the beautiful chemistry that can be invoked to stabilize some very unstable species. So, over here it is, as I said, that is everything is quite remarkable, not only this stabilization of this unstable BCP2 titanium hydride, but also of this stabilization of this unstable BH3, and these two are stabilized through by adduct formation, which again is via a non-classical bond, which is extremely rare and something which is not usually observed. So, the stability is brought about by something which itself is quite rare and remarkable, and overall this reaction thus weaves an interesting chemistry and demonstration of the fact that some of the very unstable species can be stitched together and stabilized with the help of some remarkable beautiful elegant chemistry or chemical interaction, as is found over here. So, with this we are going to finish with our discussion on transition metal cyclopentadienyl hydride complexes and move on to transition cyclopentadienyl transition metal halide complexes. So, these halide as halide ions sort of closely resemble the hydride ions because they are both two anionic 2 electron ligands. X minus halide ions closely resemble H minus hydride ion as they both are anionic 2 electron ligands. Now, these unlike the transition metal cyclopentadienyl hydride complexes, halide complexes are however more common, and a large variety of transition metal cyclopentadienyl halide complexes have been synthesized, mainly particularly as a precursor to many other complexes. So, as a result these halide chemistry has been extensively developed. To illustrate this, I am going to write out some of the examples of such transition metal cyclopentadienyl halide complexes. For example, CpMCl2, M can be for titanium, vanadium and chromium, okay, or CpMCl3, again titanium, zirconium, have vanadium, CpMCl4 for niobium, tantalum, molybdenum, then Cp2MCl2 for titanium, zirconium, hafnium, vanadium, molybdenum, tungsten, Cp2MBr2 for niobium, tantalum, and Cp2MCl for titanium, vanadium, also Cp3MCl for thorium and uranium. Now, what is evident over here, that a large number of transition metal cyclopentadienyl halide complexes can be obtained, and they can start of the formula having a single cyclopentadienyl with different chlorine ligands, which can vary from 2, 3, 4, or for dicyclopentadienyl ligands having 2 or mono or halide ligands, as well as for tricyclopentadienyl transition metal halide complexes, where 3 CPs are there, and these are usually observed for bulkier or more bigger F block elements. So, these cyclopentadienyl transition metal halide complexes provide an important foothold for conversion to other type derivatives of transition metal cyclopentadienyl complexes. Now, before we look into the reactivity of transition metal cyclopentadienyl halide complexes, let me just now briefly go over some of the preparative methods that are available for preparation of these transition metal cyclopentadienyl halide complexes. Now, if one were to look at the strategy used for preparation of these cyclopentadienyl transition metal halide complexes, it seems very simple by the fact that these are usually obtained from transition metal halide precursor with cyclopentadienyl reagent. I will illustrate this by the example of TiCl4 plus twice of sodium Cp in THF at 25 degree centigrade, giving rise to C5H5 whole 2 TiCl2 plus twice NaCl. Similarly, the reaction of TiCl4 plus BCP C5H5 whole 2 TiCl2 in xylene at 130 degree centigrade will undergo the ligand exchange reaction to give two molecules of C5H5 TiCl3. So, what we see is that there is a ligand distribution happening from within TiCl4 and C5H5 whole 2 TiCl2, such that one of the C5H5 ligand moves over from this molecule onto this, and in return one of the chloride ligands move over to this molecule. So, this is a ligand exchange reaction happening over here. There are other examples also of such ligand exchange reactions that occur, and I am going to give another example of the same for vanadium. So, here the reaction is between C5H5 whole 2 vanadium plus C5H5 VCl2 vanadium chloride, giving to two molecules of C5H5 whole 2 VCl. So, in this case this is vanadium 2 and this is vanadium 4. So, not only this is example in which not only this ligand exchange occurs similar to the one over here, but also there is a redox chemistry going on over here, in which one vanadium 2 center reacting with another vanadium 4 center to give vanadium 3 in the product. So, here this is sort of conproportionation where vanadium 2 and vanadium 4 giving rise to vanadium 3 along with the corresponding ligand exchange reaction. Another example of this involves reaction of C5H5 whole 2 chromium plus CCl4 at 0 degree centigrade give C5H5 chromium chloride. And another example of this preparation is the reaction of C5H5 whole 2 molybdenum hydride plus CH2CHCl3 chloroform at 60 degree centigrade, giving C5H5 whole 2 MoCl2 plus 2 molecules of CH dichloromethane CH2Cl2. So, in the last two sources we see that CCl4 as well as CHCl3 acting as a chloride source in preparation of these cyclopentadienyl transition metal dihalide complexes. Now, with this we sort of see that the preparative methods used for preparing these transition metal cyclopentadienyl halide complexes are also not very many, as there are only 2 or 3 types of classes of reactions which results in formation of these complexes. Now, we are going to look into the structure and bonding and structure and reactivity of these complexes. To begin with, we will be looking at complexes of the type BCP, CP2, M, Cl2, M can be titanium, zirconium, hafnium. One of the reasons for starting with these compounds are these are air stable and also have been structurally characterized. So, these are easy to handle air stable compounds and all of them have been structurally characterized. So, let me just draw the structure of these complexes CP So, what we see is that these CP are in tilted orientation and the 2 halides are there. The geometry of these complexes are pseudo tetrahedral and the angle at the middle is around 129 degree between the 2 CPs and 95.2 degree between the 2 halides, and this metal can be the metal can be titanium, zirconium and hafnium. So, what we see is that even though the dihalide CP BCP MCl2 dihalide is monomeric, BCP2 M M equals MCl, M equals titanium is however dimeric. Let me just illustrate this. And through the synthesis first, this compound is prepared by the reaction of 2 TiCl3 plus 2 magnesium Cp2 giving so this dimeric and that has a bridging carbonyl. Now, the interesting thing about this compound is that this is paramagnetic with a paramagnetic D1 system. There is the magnetic susceptibility measurements shows singlet and triplet states. Magnetic susceptibility measurements consistent with singlet and triplet states. So, which suggests weak interaction. So, this suggests weak intramolecular titanium D1 interaction. So, this is kind of a neat example where we saw that when this is bis-halide, these are monomeric, but in the dimeric when it is monohalide, bis-Cp titanium monohalide, which is dimeric in nature with the bridging carbonyl, and that each of the titanium center is paramagnetic with single electron, they can mutually couple, and there is interaction going on which can be seen in magnetic susceptibility measurements. Now, with this I am going to conclude today's discussion on transition metal cyclopentadienyl halide complexes. Today in particular, we have looked into some of the interesting reactivity patterns of transition metal cyclopentadienyl hydride complexes, where the unstable bis-Cp titanium hydride species was stabilized by reacting with BH3 through another very interesting 3-center 2-electron non-classical bond. Subsequent to that, we have looked into various transition metal cyclopentadienyl halide complexes, their preparatory procedures, which are not very many, and were mainly the treatment of metal halide precursors with sodium cyclopentadienyl reagents, anions, or some ligand rearrangement or conproportionation reactions. We have also looked into the structure of this kind of transition metal halide complexes, and what we had seen that bis-Cp transition metal halide systems are mainly pseudo-tetrahedral, whereas when they are 3 coordinated, for example, bis-Cp transition metal halide, they are dimeric in nature. We have looked into particular example for titanium and saw that they make interesting dimeric compound which has this metal D1 interaction, which can be picked up in magnetic susceptibility experiments. So, with this I would like to conclude today's discussion on transition metal cyclopentadienyl halide complexes. We are going to be discussing these half sandwich complexes of transition metal cyclopentadienyl halide in more detail in next lecture, and I thank you again for patiently being with me in this talk, and I look forward to being with you in the subsequent lecture. Till then, goodbye and thank you.